Rathan Babu, working as assistant professor in the Department of Aeronautical Engineering, and I'm going to deal with the course computational dynamics. And today's topic, let us see what is the convergence and stability and consistency of a numerical scheme. Okay, basically, these three are very important for a particular numerical scheme, and this will decide whether the simulation what you have performed, whether it is correct, let's say inaccurate or accurate, whether it is giving a closed form of solution or not. So these things actually we can come to know. So let us look for the stability of a numerical scheme, and let us see how the stability varies. And there are some criteria for the stability, von Neumann stability. Okay, so for the von Neumann stability, like there will be some conditions in order to be satisfied. So we'll look for those conditions, and before that, so we need to see how the convergence criteria is coming, and how the consistency is coming. Then we will see the von Neumann stability. Okay, so basically the convergence of a numerical scheme. So let us take a equation. Let's say so dou u by dou t plus alpha into dou u by dou x is equal to 0 is a only wave equation. So here this equation basically has to be solved using appropriate numerical techniques. So the numerical technique whatever we are using, so whether it is stable, consistent, or whether it is converging or not, we need to see. So let's say the convergence criteria, we will actually give it to the simulation to stop it. So when let's say you are using this uh, equation to solve a fluid flow problem using finite difference method. So let's say a forward in time, forward in space method. So what we have, let's say u of I n plus 1 minus u of I to the power of n divided by delta t plus alpha into u of I plus 1 to the power of n minus u of I to the power of n divided by delta x is equal to 0. So this is what we have. So what is unknown we have? So this is the unknown term which we have. So u of I to the power of n plus 1 will be equal to, so what do we have, like u of I to the power of n minus alpha into delta t by delta x into, so u of I to the power of n minus u of I to the power of n is equal to 0. So this is the equation which you have. Now, so basically the convergence. So the convergence criteria has to be seen every time. So let's say you are solving this equation at time t is equal to 0 seconds. So sorry, time t is equal to 0 second, we will initialize the simulation. So initialization is nothing but, so let us actually have to give some initial conditions and boundary conditions for a particular domain and start solving the problem. So let's say, let us take the 1D thing. So here you have the boundaries, let's say. So for these boundaries, like you will be applying some boundary conditions. So and these initial values are applied at these points. So based on the boundary conditions and initial conditions, the problem will start getting solved actually. So these here you can see on the right hand side you have all known values. So these known values are coming initially from initial condition at time t is equal to 0 and the boundary condition. Okay, so let's say you have time t is equal to 1 second. Fine. So let's say a time t is equal to 0, you have u of 1 at 1, let's say. So I, let us take I is equal to 1, n is equal to 1. So what will be the, so u of 1 and 1. So u of 1 in the sense, so here what I'm referring is like, so the velocity at the second next time level, at a particular grid point. So let us take a particular grid point 1. Okay, so you have the time levels. Let's say this is time level t is equal to 1 second. So another time level t is equal to 2 seconds. Okay, so on t is equal to n seconds. Fine. So what we do is like, so basically it's u of uh, 1. So let's say 2 minus u of 1 to the 1. So basically if the difference is less than the convergence thing, so basically if it is less than the criteria which we give the error, so basically this epsilon value is the convergence criteria or the value which we define. So if you think this would be 0.01, so then this can, if the difference is less than 0.01, the simulation will stop. Okay, so if you are taking, let's say 0.00001, so basically 1e minus 4, so 1e minus 5, 1e minus 6. So the meaning is the velocity at this particular grid point, so is having an initial value. So it after certain time, so you have another value. So the difference between the initial and the next value, if it is coming less than the particular error that we assign, then we can say that the simulation has convergence. So the convergence criteria has to be seen to stop the simulation, so which we impose it. And for simulation to converge, so basically we need to see the consistency and stability of a numerical scheme, so which we will discuss. But now let us get an idea of what is convergence actually. So what we have here, so let's say the unknown value here u of I to the power of n plus 1, and so basically this is at one time level. At next time level, so you will have the u of let's say this is n plus 1. Next say you have another time level. Okay, so the difference between those two, if you are having certain error like less than that certain error which you have specified, then you can say that simulation has got converged. So this is one of the methods to see the convergence criteria actually. So generally what we do is like, so generally what we do is like we will have flow properties. So basically you have pressure, you have velocity. So let's say u velocity, v velocity, w velocity. So and you have temperature. So in the simulations, so let's say you are having ANSYS, or let's say you are having open form. So depends upon the tool that you use, the convergence criteria is different. So let us talk in general. So this iteration, so let's say you have the time. Okay, so here as the time progresses, so the iterations number. So basically, so what happens? So the convergence criteria. So whatever we need to see, we have to see it actually. So this is called residue. Okay. So basically, the residue or the epsilon which we are talking. So the residue or the epsilon is like user defined. So let's say, so this one, let's say epsilon will be u of n plus 1 minus u of n. So basically, uh, this is what we have. So the value of velocity at a particular grid point at the next or the next time level and initial time level. So if you take the difference, so you'll get some value. Okay, of s. Let us take, so s of I which we initialize. So epsilon of I. So let us take this one. So the epsilon of I, if it is greater than epsilon of s, okay, so then we can see that one. But if epsilon of s is greater than epsilon of I, then you have to keep on running the simulation. Okay, so here what I want to say is that, so the residue here what we specify is basically 1e minus 4, 1e minus 5, 1e minus 6. So based on the solver that we take, and based on the equations we solve, and based on the fluid flow problem that we are getting. Okay, so if we are having only the incompressible flow with no heat transfer, so the residues what we observe is for u velocity, v velocity, w velocity, and pressure. So in the sense, basically you will take so continuity and momentum equation. So basically it's continuity and momentum error. So the residue will be for continuity and momentum. So in the momentum, so since it is a vector, so you have x momentum, and you have y momentum, and you have z momentum. So these residuals, let's say, so you have, let us take this is for continuity, and this is for x momentum, and this is for y momentum, and you will get one more thing, this is for z momentum. Okay, so basically if it is a 3D incompressible flow problem, so we have these, like we have these equations: continuity equation, momentum equation. Momentum equation will be of 3, so total 4 equations. So the residue things you will be observing for these. So some things, let's say in ANSYS, in a graphic interface, you will be seeing this residue versus time. So in the other, let's say open form, so you can actually see, or any, even in the ANSYS also you can see the residue script. So there also you can see what will be the value of velocities at each and every time level. Okay, and what is the error associated with that? So basically the velocity error which is going less than 1e minus 5 or 1e minus 2. So these things, so you can see in the residual script also. So in the graphic interface, like you will be seeing the continuity, momentum, energy equation, residues. So the continuity and momentum will be there for incompressible flow, whereas for the compressible, or let's say whereas incompressible heat transfer, so the another line will be coming, so which is like you can say the energy equation. So since the momentum is vector, you have x momentum, y momentum, and z momentum. So continuity and energy are scalar, so therefore you have these 5 curves, okay, residue plots, which you will be seeing in the ANSYS, okay, let's say ANSYS graphic interface, or CFX, whatever you can take. Okay, so now basically what we have seen is convergence. So after the convergence, so the important thing is for before, like what do you say, not like after, so before the convergence. So when we are taking a particular numerical scheme, so we need to see the consistency and stability. Okay, so let us see what is consistency. So let's say you have this equation again, minus u dou by dou x is equal to 0. Okay, or let us take this as alpha. Okay, so what we have, so this is a PDE equation, partial differential equation. So this partial differential equation, so we need to actually discretize it and write a discretized equation. So how do we write it actually? So u of I to the power of n plus 1 minus u of I to the power of n divided by delta t minus alpha, so into u of I to the power of u of I plus 1 to the power of n minus u of I to the power of n divided by delta x is equal to 0. So let's take this one. So now, in order to check the consistency of a numerical scheme, so what we do is like, so we have this equation. So let's say, like we have this equation, entire equation. So we will actually take each and every term in this equation. Let's say u of I to the power of I plus 1 to the power of n. So this term, let's say u of I plus 1 to the power of n. So here, if we are writing in the form of subscript which is I and superscript which is n. So basically n tends to time, so I tends to space which is x. Okay, so if we write in the form of Taylor series of expansion, so u of x plus delta x. So basically, this is what we have at a time n. Okay, so that will be u of x plus dou by dou x of ux into delta x plus dou square u of by dou x delta x square. So this is what we have. So similarly, so what we do is like we are doing the reverse engineering. So basically, here we will expand each and every term. Okay, so we will write this one as u of x. So this one you will write off here you will expand with respect to time. Here, what is it? We are expanding with respect to space. Okay, so let's say when you are expanding with respect to time, so t of delta t. Similarly, u of t plus dou by dou t of u of t into delta t. Okay, so plus dou square u by dou t square u of t into delta t square. So here so on, here also you have so on. So basically what we have, so we have so many other terms. So what we do is like we will substitute this one in this equation, we'll substitute in this one in this, sorry, we'll substitute this term here, substitute this term here. So u of I to the power of n, u of I to the power of n. So basically, like no need to expand here. So now when we substitute these equations, okay, so when we substitute these equations, so what we are having, so we will have again this partial differential terms. So what we are doing is initially we have a PDE, okay. For that PDE, what we are doing is like, so we are writing a discretized equation, okay. So that discretized equation, whatever we have, so we need to actually reframe it again using Taylor series of expansion. So using Taylor series of expansion, like let's say you have the terms, so u of I plus 1 to the power of n and u of I to the power of n plus 1. So here these two terms are taken. So basically here u of I plus 1 to the power of n and u of I to the power of n plus 1. So we have expanded in terms of Taylor series of expansion and substituted here. So these u of I to the power of n will be like u of x to the power of n, or you can take u of x. Okay. So what we do, like we will substitute all these entire terms and we see with whether the original PDE is obtained or not. After substituting these equations, let's say 1 and 2, sorry, let us take this is 1, this is 2 and this is 3. So when we take this equation 2 and 3, so we will substitute the equations 2 and 3 in equation 1. Okay, and you will apply a limitation delta t comma delta x or delta square or delta t tends to 0. Okay, so when you apply this condition, you have to obtain from this equation the original form of PDE. Okay, so then if you are getting that original PDE from the discretized equation, then the numerical scheme what you obtain is called consistent. Okay, so the consistency of a numerical scheme is between the PDE and the discretized equation actually. So partial differential equation what we have and the discretized equation. So how we are getting? So basically it is the numerical scheme which we take it. So if we take forward in time, forward in space, whether that forward in time, forward in space numerical scheme is able to give a consistent scheme or not. Consistency is seen by again this re-verification. So let us take this procedure you can follow for any other equation. So let's say you have the heat transfer dou by dou t. Okay, so diffusion equation. So here, so the same approach will be there. So t of I to the power of n plus 1 minus t of I to the power of n divided by delta T. So this is a temperature equation, minus alpha into T of I plus 1 to the power of n minus T of I to the power of n divided by, sorry, this would be, this is not forward difference, minus 2 of, so you can see here the equation complexity has somewhat increased, you can see. So here what we have, so basically the terms which we need to expand is T of I to the power of n plus 1, T of I plus 1 to the power of n, T of I minus to the power of n. Okay, so what we do, so basically here T of I plus dou T by dou T to delta T. Okay, let us say time here, plus dou square T by dou T square into delta T square by 2 factorial, plus dou cube T by dou T cube to delta T cube divided by 3 factorial, plus so on this is all. Similarly here what we have, so here since it is in terms of time, so we have time term. So again what we have, this is T of x, because I we have taken it as x, plus dou T by dou x into delta x by 1 factorial, so basically it is 1 factorial, plus dou square T by dou x square into delta x square divided by 2 factorial, plus so on, let's say. So here you have the term T of x minus dou T by dou x plus delta x by 1 factorial, plus so on. So you have the odd terms are negative. Okay, so this equation, so let's say this is 1, this is 2, this is 3, and this is 4. So what we do, we have 3 terms actually. Here you can see 1, 2, and 3. So these 3 terms actually, we what we need to do is like we need to expand in terms of Taylor series of expansion. So when we expand these three terms in terms of Taylor series of expansion, so what we get, 2, 3, 4 we get. So again we'll substitute in this equation. Okay, so here what we write, T of I to the power of n. So basically let us take, so this one has T of time, and here you will take space. Okay, however here you can see that you have this one will get cancelled, so the remaining terms, so dou T by dou T will be there, and these remaining terms, so you have this dou square T by dou x square. So here the criteria is, so when we apply equation 2, 3, 4 in 1, so what we need to get, so the original PDE has to be obtained. This is original PDE. So basically what is this scheme? Forward in time and central in space. Okay, so FTCS scheme. So basically this FTCS scheme, whether it is consistent or not, so will be evaluated by this procedure. So when you get, so when you apply, sorry, delta t square delta x square tends to 0, then when you get the original PDE, so then whatever the equation or the numerical scheme that we have is consistent. Okay, so basically this consistency has to be evaluated for a given numerical scheme. So if the numerical scheme is inconsistent, then you cannot use. Why? Because if the numerical scheme is inconsistent, so what happens is like you have error. So basically the error. So basically, let us take this, if this error, whatever we have, so error versus time, if it is growing with respect to the simulations, okay, then whatever the values that you are getting, so will be incorrect and simulation will collapse. So, or the numerical scheme will collapse actually. So basically the stability. So stability, so consistency, stability. If you are actually satisfying, then convergence will be automatically met actually. So the stability of a numerical scheme is evaluated using a, linear numerical technique. So basically, one Newman linear stability actually. So those are applicable for linear equations. So what we do is the numerical equations is the linear, and whatever the partial differential equations are there, so we'll linearize them and we'll form a discretized form equation. Then we will actually apply the technique of von Neumann stability and evaluate the error. Okay, so the stability, so basically consistency we have seen how we will check it for consistency. So next class we'll be seeing how the stability is also like evaluated. So stability using the von Neumann stability. So when you are looking at stability and consistency, so basically this one and this one, so the stability and consistency when they are meeting each other, so then automatically convergence will be met for a numerical scheme. Okay, so in the next class we'll be seeing what is the stability and so using von Neumann technique, and we will conclude the consistency, stability and convergence topic. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.